Section 7.6 is exponential functions. I can evaluate and graph exponential functions. Big idea for this section. Some functions model an initial amount that is repeatedly multiplied by the same positive number. In the rules for these functions, the independent variable is an exponent. If we look at the take note on page 453, it tells us an exponential function is the function of the form y equals a times b to the x power. Okay, so here in an exponential function, our variable is in the exponent. If all the x values in the table have the same common difference, which means we add or subtract to the same number, and all the y values have a common difference, the table represents a linear equation. If all the y values have a common ratio, which means we're going to multiply or divide by the same number, then the table represents an exponential function. And that's because if we have the same difference, okay, we show repeated addition with multiplication, linear, something like y equals mx plus b. Okay, that repeated multiplication is multiplied by our x values. But when we have a common ratio, that means that we have multiplication, and we write repeated multiplication as an exponent. So here we'd have something like y equals a times b to the x power, where that repeated multiplication is displayed in our exponent. Identifying linear and exponential functions here. Does the table or rule represent a linear or exponential function? And why? So here we got to check our x's to make sure we're going by the same amount each time. 0 to 1 plus 1, 1 to 2 plus 1, 2 to 3 plus 1. So there we're increasing by the same amount every time. Now we're going to check our y values. To go from -1 to -3, we have two options. We can multiply by 3, or I can add a -2 or subtract 2. Now we check from -3 to -9. I get there by multiplying by 3, so -2 is out. Let's do it one more time just to double check. From -9 to -27, I can multiply by 3. So since we're multiplying here, this is a common ratio, and we talked about common ratios and common differences a little bit in our sequence chapter earlier. But here we have a common ratio, which means this is going to be an exponential function because we have repeated multiplication, which we represent with an exponent. In B here, this is going to be linear. Okay, we can graph this in a line. Intercepts at 0, up 3 over 1, up 3 over 1. Also, it's only exponential if our variable is in the exponent, but here it's not. Okay, it's in line with the rest of my numbers, so it's a linear function. Feel free to pause here and give these a try if you'd like. Does the table or rule represent a linear or an exponential function? So here, 1, 2, 3, 4, I increase by 1 every time. I'm good there. In my y's, I go from -1 to 1 by adding 2 or multiplying by -1. To go from 1 to 3, again, I'm going to add 2. And from 3 to 5, I add 2. So here, because I'm adding each time, I have a common difference. And I show repeated addition with multiplication. So I'd have like m times x plus b. This is linear. In B, my variable is in the exponent. So when my variable's in the exponent, I have an exponential function. In example 2 here says, suppose 30 flower beetles are left undisturbed in a warehouse bin. The beetle population doubles each week. The function f of x equals 30 times 2 to the x power gives the population after x weeks. How many beetles will there be after 56 days? So here we're going to pick out the important stuff. It tells us my function, f of x equals 30 times 2 to the x power. it tells me that x is in terms of weeks. It also tells me I have 56 days, but I can't have days, I need weeks. So we need to switch from 56 days to weeks. And I do that by multiplying by a conversion factor. There are 7 days in 1 week. Days cancel. I multiply across and I get 56 divided by 7, or 8 weeks. And some of you might have done that in your head, and that's fine because this is a conversion that we use quite a bit. And days and weeks are pretty ingrained into our knowledge base. But if it's something that we're less comfortable with, don't be afraid to set up that conversion factors. We need weeks on top because we're looking for weeks, and we need days on the bottom so the days in the numerator and the denominator will cancel. So now that I know 8 in terms of weeks, that tells me 8 is my x. So I'm going to find the value of my function for 8 weeks. Okay, I just plug in an 8 everywhere I see an x. And then here, all we do is calculate. So the value of my function after 8 weeks, I get 7,680 beetles, which is actually pretty gross if you think about it. I started with 30. After 8 weeks, we have 7,680. No thanks. Feel free to pause here and give this a try if you'd like. Now, an initial population of 20 rabbits triples every half year. The function f of x equals 20 times 3 to the x power gives the population after x half-year periods. How many rabbits will there be after 3 years? So again, we have our function f of x equals 20 times 3 to the x power. And x is in terms of half years. Here I have 3 years. So we need to think, how many half years is that? Well, in 1 year, there's 2 half years. So 3 years. And in 1 year, there's 2 half years. Think about it in terms of school. In 1 year, there's 2 semesters. Same idea. A semester is half of a school year. Okay, our years cancel. I have 2 times 3, or 6 half years. And again, you may not have had to set up conversion factors there, guys. That may have been one that you guys were just comfortable making the switch from, and that's okay, as long as you can get to the 6. So here we have 6 half years. X needs to be in terms of half years. So I can find the value of my function after 6 half years by plugging in 6 for all of my x's. Here, I get 14,580 bunnies. In example 3, we're going to graph an exponential function. Here we're going to use a table of values. And when we do our table of values for exponential functions, we just about always use the values -2, -1, 0, 1, and 2. Because when we start dealing with exponents, our numbers can get very big or very small fairly quickly. So we want to be careful and make sure that we're using numbers that are going to give us values that are fairly easy to graph, or at least more reasonable than if we plugged in like 10, for example. So here, now that I know my x values, I'm going to plug them into my equation. Everything else is staying the same. So my 3 times my base is staying the same. 3 times my base is staying the same. The only thing that's changing is instead of an x, I'm plugging in my x values. So here I raise it to the negative second power, negative first power, 0, 1, and 2. So here, I can simplify. I take my 3. I don't have to do anything with that. It doesn't have a negative exponent, it doesn't have anything like that. Nothing we have to do to simplify it. 2 to the negative second power, though, to make it be a positive exponent, I move it to the denominator and change its sign. So here I'm going to have 3 over 4. Same thing here. The only thing I need to change is my negative exponent, so I drop it to the denominator. My 3 doesn't have a negative exponent though, so it stays. My 2 drops down and my exponent becomes positive. So I have 3 over 2, which is 1.5. 2 to the 0 power is 1. Anything to the 0 power is 1. So 3 times 1 gives me just 3. 2 to the first power is 2. Multiply it by 3, we get 6. 2 squared is 4. Multiply it by the 3, and we get 12. So here I have negative 2 to the 3/4 power. I have negative 1, and then I have 1.5. I have 0, 3. I have 1, 6. And I have 2, 12. And we're going to connect these dots as best as we can. Be careful though here at the bottom. We're not going to cross the axis there. We're not going to cross our x-axis. Our y value is never going to be 0 because we don't have a 0 to multiply by. And I'm not multiplying by an x. What I'm doing here is I'm taking 2 times itself. So since I never have multiplication by x or by 0, I can never get 0. So we're never going to cross the axis there. That's called an asymptote. And we'll talk about that more as we get a little bit further. Graph of each function here. Again, I'm going to use my table of values. Negative 2, negative 1, 0, 1, and 2. I keep my function the same. I'm going to change the 0.5 to a half though, times 3 to the x power. And when I multiply here, the 3 to the x power is in my numerator, and the 2 is in my denominator. It's just another way to write it that's a little bit easier when we try and calculate, like if we don't have a calculator. If you have a calculator and want to just multiply by 0.5, you certainly can. But I'm going to simplify here. Now, I'm going to plug in my exponents. So I'm going to take 3 to the negative second power over 2. 3 to the negative first power over 2. 3 to the 0 power over 2. 3 to the first power over 2, and 3 to the second power over 2. When I simplify, any negative exponents, I have to move to the denominator and make positive. So here I get 1 over 2 times 3 squared. 3 squared is 9, and I get 1 over 18, which is approximately 0.05 repeating. Same idea here. I have 3 to the negative first power. I move it to the denominator in order to make my exponent positive. 2 times 3 to the positive first power, which gives me 2 times 3, or 1/6, which is approximately 0.16 repeating. 3 to the 0 power is 1. I don't have to move that to the denominator. 3 to the 0 power is 1. Anything to the 0 power is 1. So here I just get 1/2. 3 to the first power is just 3 over 2, or 1.5. 3 squared, 9 over 2, which is 4.5. And these aren't approximate, those are exact because I used the repeating. Now when we graph this, guys, it's not going to be perfect. We're not going to know exactly where 1/18 is, and we're not going to be able to show that on our graph. We're just going to get as close as we can. So I'm going to say it's about right here. And then 1/6 I'm going to say is about right there. 0/2, now we're getting a little bit closer. 1, 1.5, again a little bit easier to graph. And 2, 4.5. And we can connect these dots, not crossing the axis.